It's the writer, not the floor. Here, I'll throw it out for you.
That, you know what? I just missed. I thought the trash can was right over there. Sorry. On me, right?
Yeah.
I was gonna say.
I'm really sorry.
It's right here.
Hi, Frail.
So rude.
I know, I'm really rude today. I'm really sorry.
She doesn't get a stapler.
At least I didn't say anything about it.
Just stapler.
Right?
Throw a stapler at her.
No, it's slightly ill-fitting, but what do you want me to do, okay? Not made of gold. Just kidding. Alright, I hate this lesson. Put that out there.
Derivative inverse.
Because the y is a lot more complicated than what you're supposed to actually do. So we have to take a few days to talk about derivatives of inverses. And tomorrow we'll actually take it a little bit easier, and it'll just be derivatives of, like, the inverses of polynomials. It's not quite as bad. The derivatives of inverse trig. So, like, what's the derivative of arcsine? And the derivative of arccosine, and arctangent, and blah, blah, blah. Do you even remember what arcsine is? And arctan, and all that. It is ugly. So do you remember from pre-cal, like, let's look at the sign. If y equals the sine of x, that's like your original function. So it goes like this, blah, blah, blah. If we want to talk about its inverse, the inverse sine of x, do you remember what makes something an inverse? There's a couple different ways to define it. One is that, like, f of the inverse of f of x equals what?
Y equals x. Or
Equals-
it's flipped over y equals x.
Not even that, I'm sorry. I mean, like, if I compose them, like, if I use f to denote the function, and f to the negative first to denote the inverse, do you know what I would get? No.
X.
X.
There.
I get x. It's like saying, like, x squared is square rooted. X squared, maybe, say your original function, the square root of x is its inverse. They undo each other and give you just back to x. Just like the sine of the arcsine of x equals x. Okay, the sine and the arcsine or inverse sine, they undo each other. So arcsine, inverse sine, I'll use interchangeably. They both mean the same thing. And it can be written with a -1, or it can be written as literally arcsine. And either way, if I compose the two, they equal x. The other thing that's true about inverses is, like, they're reflections of each other. Do you remember over what?
Y equals x.
Over y equals x. So if I had, I'll take this example because it's easiest. X squared, let me just take the positive half of it, and the square root of x, take the positive half of it. Those are inverses, and they're reflections over the line y equals x. I couldn't include both halves of the parabola because then the inverse would have both halves and then would fail to be a what? A function. So when we talk about these things being reflections over the line y equals x, the original function has to pass what's called the, what, do you remember? The horizontal line test. If the original function fails the horizontal line test, its inverse won't be a function, because then its inverse will fail the vertical line test. So there's a little bit of that going on. The third thing that makes, or the third thing that's true about inverses and the original functions is that the domains and ranges are switched. So for example, x squared to the square root of x, the domain here, actually I don't know if this is going to be a great example. Let's take x to the
9.
no. Well, whatever. Let me just take this. The domain of this is going to be negative infinity. Ooh, that's an 8. Negative infinity to infinity. And the range is going to be 0 to infinity. Whereas for this, the domain is 0 to infinity. And the range is,
Yes.
if I have a plus minus, let's just pretend it's not a function, whatever. The range is negative infinity to infinity. So they switch. The domain of one is the range of the other. The range of one is the domain of the other, blah, blah, blah. Okay, that's your 5-second recap of inverses. The only part of that that really matters for us is this idea that they are reflections over the line y equals x. Because when we do this, we want the inverses to be functions. We don't want the inverses to be relations. So remember what we did in pre-cal last year? We cut it off. Remember we restricted these things? So remember we took sine and we said, well, if I only go from here to here, now sine passes the horizontal line test. So therefore its inverse will be a function. Do you kind of remember saying that? All that you really need to know is that each one has a restriction. So let's just go through what the restrictions are to the side so you'll know. It's not the hugest deal, but it's worth noting. Okay, so restrictions for inverses, if we have the sine of x, we're going to restrict the domain. What is this x value?
-1. Pi over 2.
Pi.
Pi
Over 2.
pi over 2. We'll go from pi over 2, or negative pi over 2 to positive pi over 2. Do you see why again? I'm doing that so that sine is kind of covering every y value only once. So go from negative pi over 2 to pi over 2, then that means it's going to pass the horizontal line test, which means its inverse will pass the vertical line test. If I have cosine of x, looks like this. I decide to restrict it from here to here. So again, I only have one y value for, or touched. Or I'm sorry, every y value is only touched once. So this is going to go from 0 to what?
Pi.
I. And tangent splits itself over the y-axis with its asymptote here and here. So I can actually take one whole period of tangent because it never fails the horizontal line test within the whole period. So I can restrict that just to one period's worth, which will be negative pi over 2 to pi over 2. So as I'm doing these problems,
Pi over 1.
No.
Oh no, it's a
I'm going to just keep it in mind that they have these restrictions. Okay. So who really cares? This is just like a pre-cal backdrop, I guess. What we have to be able to do is take the derivative of the inverse sine of x. So I'm going to go through and prove the first one, and then we'll just go through what they all are and sing camp songs. So let's prove something. Let's see why.
Wait, let's be clear about something right now. Is a proof of this going to show up on a test?
I'm not going to be clear about it, because what if I change my mind?
You shouldn't change your mind. You should.
This isn't that hard, so you don't have that much of it. I'm not saying that.
So,
Okay. So if y equals the inverse sine of x, I have to refer to my notes. Okay. The first thing that we're going to do to be able to prove this is we're going to take the sine of each side. Because I don't know how to take the derivative of the inverse sine of x yet. I'm trying to figure out how to do that. What is the sine of the inverse sine of x?
X.
Just x. Okay, so far I've just done some like trig manipulation. I just took the sine of both sides. So the sine of the inverse sine of x kind of undoes each other and just gives you x. Any ideas? If I'm going to figure out what the derivative of y is, that's where I'm going now. What could I do? Let's take the derivative. So the derivative of the sine of y is what?
cosine of y times the
Cosine of y, good, times y prime. So this is kind of why this comes after implicit differentiation, because we have to be able to take the sine of y and first of all chain it on using chain rule, and then realize that the derivative of y is not just 1, it's y prime. The derivative of x is 1. So I have y prime equals 1 over the cosine of y. I'm not quite done yet. So I'm not going to change it to secant first, actually, only because I know the trick. So you could change it to secant of y, and that would be correct. But I kind of want to get rid of having a y here. It's annoying if I was going to take the derivative and then I have to take it in terms of y, I might not have that y point to plug in. It makes things a little bit confusing, so I'm actually going to do this. Okay. Remember how sine squared of y, I can use y if I want, plus cosine squared of y equals what?
1.
1. So what would the cosine of y be using the Pythagorean triple? If I want to solve for the cosine of y, I'd have 1 minus sine squared, and I'd square root. So I'm going to go ahead and replace cosine of y with that, which doesn't seem easier yet. So y prime is 1 over, instead of the cosine of y, I'm going to replace it with the square root of 1 minus sine squared y. Well, this is actually really helpful. So step back for a minute, because this is going really fast, and think about why could this be helpful? What could be replaced in this expression to give me a much easier way to write y prime? Better than that. Without any y's.
Plug in arc sine x for y.
Instead of, well, okay, sure, kind of. Move ahead. What is the sine of y equal to?
X.
Yeah. Just go find it. The sine of y by itself is equal to x. So I can just write this as 1 minus x squared. And that's it. And when I say, that's it, do you have any idea what we just did? Right? We took the derivative of the inverse sine of x. We never have to do all this work again, other than understand how we got to the end.
On tests.
Even on a test, I don't know. It's not that, I'm not gonna say yes or no to any of that, because I just don't know.
So that's a yes.
But what you did was, if y equals the inverse sine of x, we took the derivative of it the really long way, and now we can just memorize the rule that if we have the inverse sine of x, the derivative of it will be 1 over the square root of 1 minus x squared. The only change on here, which I don't really have in proof form, is that this does follow chain rule, in that anytime I take the derivative, I would need to chain on the derivative of whatever x is. Which does matter, and I'll show you what I mean in a second.
Please pardon the interruption. Attention freshman field hockey players. Your game has been canceled. Please do not leave class at this time. There is no game, but please report to practice after school. Thank you.
Let's say I have the inverse sine of x squared. So let's just take a derivative of it following the formula to see if it makes sense. So all I have to do is follow this formula, but realize, see my original thing? X is just x. Well, now that x is x squared. So that means that when I take, the derivative, I'm going to use this. I'm going to have 1 over the square root of 1 minus whatever that is squared. See what I mean? Whatever this is like the x in the formula. In fact, I think in the book, they use u's a lot. They make this a u. So that you start to make the distinction between, that's the formula. So whatever this is, it might not just be x. If it's x squared, I'm putting in x squared squared. If it's 4x, this would be 4x squared. Whatever that is going to get squared. Do you know what I mean? Okay. And then I have to multiply by the derivative of whatever it is. So in this case, 2x. The procedure's not that hard. The annoying part is that we have to memorize this. If I was going to totally reduce it, the derivative would be 2x over the square root of 1 minus x to the 4th. So all of whatever that happened for the last 15 minutes doesn't mean a whole lot in that hopefully, I mean, other than hopefully it like gives you a little bit more of an understanding of what inverses are about. What you really need to know is if you have to take the derivative of the inverse sign, this is the formula that you use. And you do have to memorize it. And there's 6 of them. Yeah. I know. I wish I could tell you. There have been some years where I'm like, you know what? The AP test never asks you to do this. But I've been proven wrong. And they do.
No, they don't.
We can deal with one wrong.
Yeah, you only need like a 70 on the test. You just ignore this part.
Yeah, but these are the easy ones. Like if they ask you just for a derivative of a trig function, it's a really easy problem to do if you have the formulas memorized. So here's the formulas. We got the sign. You know what, let's use u's. Let's start to get in the habit of this. You're going to see u's a lot.
Is it still over dx or
It
is
still
over
is.
du?
It's still going to be like with respect to x, but is it minus? I've never ever memorized these.
What?
Yeah,
Wait.
I don't have it memorized. I'm not being tested. I'm just kidding. But I don't. Like every year I have to kind of go through and remember them again. I'm sorry. Shouldn't have divulged that.
You're not qualified.
That was embarrassing. Okay, so the cosine one is just negative. And it's the same thing as sine, but it's negative, so that's easy. What I will guarantee you is you will see a inverse tangent one. They love asking about the inverse tangent. Well, I guess I do know why, because it's the easiest. It's just 1 plus u squared. So if you're going to memorize any of them, memorize the tangent, because it'll be on there. And then cosecant and secant suck.
Bless you.
Right? Like,
Yeah.
What is that on the bottom? Is that the absolute value?
yeah.
You proved that one.
No. Please.
Will the proof of that be on the test?
Yep.
Alright, well I'm dropping.
That's what I've been trying to get done. Just kidding.
No, you're not.
Yeah, I'm sorry.
No, you're not. You do it every year, but you keep doing it. You're not sorry.
At least they all kind of match up with derivatives.
They all
of
match
their-
up.
With their regular functions.
I hate to say it, but like I can't imagine that I would ask you to do cosecant or secant on a test. You know, before the real test, maybe we'll try to cram that a little bit just to get that formula in your head in case it comes up, because I have seen secant get asked before.
Okay, let's zoom out a little bit. So that's sine. You can pause here if you need to. It's a video. And then there's tangent. Okay. And then we go to the next one. Which those are confusing, but those are absolute value bars. And then cotangent. Okay, bye. Shit, yeah, I have like a scarf and
I said Jimmy actually.
oh, Jimmy. Let's look at Jimmy.
Zoom in. It's looking good today.
You can pause this too if you need to.
Pause and
Pause.
okay, so there's not a whole lot to do. Let's just do like one random example. I always hear Monica's pencils like shuffling.
I'm sorry, it's so nice though. I hit them all in
green one. Got it. And then this one's the blue one. I would get confused.
That might help me memorize stuff actually.
What? Probably
If I had it color, just in different colors and
It
stuff.
just helps you see what's important on the page. Like, this is
Yeah.
examples, this is self-study.
Yeah.
That's what I did.
Good. Alright, try this. There's nothing complicated about taking these derivatives. It's just following a stupid formula.
Except it's secant.
Except that's stupid formula.
Right.
Right, the hard part is that stupid formula. We'll try two things, actually. Can you guys see the green okay? On the board that does not erase?
Yeah, it's not bad. It's just,
Eric, does this drive you crazy? Doesn't it make you nuts when boards don't erase?
yeah, I don't like it.
Just Eric, no one else.
I remember from last year, like if I left like a little thing, wasn't that you who was like, could you
Oh my
get that?
god, that's
Yeah,
really bad.
you get that, yeah.
But no, but like, this is better than that when you just leave one little thing. Oh.
Do my answer in a different color. Did I actually do it?
Yep.
I haven't memorized anything. Actually, you might see on a test, like if this is an a multiple choice problem, you might see it without the bars, and you might be wonder like, oh, that's not right because of the bars. But 5x to the fourth, can that ever be negative? No. So they'll probably take the bars away because it's redundant. You want to know that if you saw that as an answer, you don't think it's wrong because it's right. It's just it doesn't have the bars. It doesn't need them. Okay, so that's it. I mean, that's taking the derivative of. What's that?
That's the answer.
That's the answer. I mean, I guess I can go reduce now that I don't have the bars. So, I guess you wouldn't see it like that on the test. You'd see 4 over x. But, that's it. Is that okay? Try the second one.
Is this in meters per second?
I don't know. Particle moves along the x-axis, probably more like centimeters per second or something. Did I do it right? What's 17 times 8?
be 1/32 on the top.
Mental math is struggling.
Not 1/8.
I think I have it right.
Oh no, you're right. You're right.
136.
Hello?
Yeah.
That's okay. Yeah, but that's okay. Okay. Okay, well, yeah. Bye. Mike, you should remember to pick up work for your brother before you go home. Would you have forgotten?
Yeah.
I don't know, did I get it right? Did I do something wrong?
136.
I got 131.
What's 17 times 8? It should be
I got
6. 136.
Jimbo.
Jimbo. Don't worry.
Isn't it over 1 plus t squared? Not 1 plus t.
Root T squared.
Root.
But root
Oh,
T
root
is
T
like
squared.
the U.
Right, right.
Yeah.
Can you just do tan? Oh, is it arctan of 4? What was that?
Can you do the arctan of 4? That's going to tell you the position.
Well, no, I mean like the
Take the derivative of the arctan
yeah,
of
so
4?
it'll be this. So it'll be just plug in 4.
I guess since I don't have to chain on anything, I can do that. If it was something different where I'd have to chain on, then no. But yeah.
Well, if you don't chain on it, then why do you want to 17?
Actually, no. If you just take the derivative of the arctan, did you try it? You don't get that, do you?
You get 1 over 17.
You just get 1 over 17? Not 1 over 136. Yeah, so no. Because what you're doing is if you just plug in the 16, you're missing like the derivative of that part. That's what you're missing. So no, you can't.
Alright.
Yeah.
If it doesn't give you the value of 2, would you have to take the t to the negative 1/2 of the denominator?
I'm sorry, say that one more time. If it doesn't give you what?
The t value for 16, you would have to solve that. Would
Sure, then I'd probably go from here. I'd have 1 over like 2 root t
right.
all over t plus 1. Then I'd have 1 over 2 root t times t plus 1.
Okay.
That's how I would leave it. Okay, to get that fraction out of the fraction. Okay, do you have questions? Okay. The homework.
There's a football game tonight. I'm not gonna do it.
Well, that's why it's this one's due Tuesday. You
Oh,
have a
great.
whole extra day over the weekend. It's Columbus Day.
Columbus is kind of an important person here.
It's actually not that important.
Wait, what's happening tomorrow?
No,
I think
he's
it's just
actually
like-
an idiot. So
Yom Kippur.
I don't like him.
What?
Yom Kippur is Friday, right? That's why the football game's today.
Yeah.
Why do we have off?
Why do you have off?
Why don't we?
Oh, because I think it starts at sundown on Friday,
Yes.
Yom Kippur, so it goes into Saturday.
You have Monday off, right?
Yeah, that's for Columbus Day though, not for the Jewish holiday. All right. Yay, calculus.
It looks like it's a 162.
Oh, it's like a plus. I think it continues on like it might be like
162,
multiple pages.
9, 11, 15, 17, 19.
It's an equation.
Okay.